I'd like to talk about heights and vertical datums because, of course, the world is not simple. We don't have an integrated set of vertical measurements that integrates well with our horizontal measurements, but it's really unavoidable because of the dynamics and shape of the Earth. We have three surfaces for measuring heights. There's the ground surface, and that's typically the height we're measuring to, although if we're flying a plane, we're interested in the plane's flying height, of course. And then there's the ellipsoid, this mathematical surface we use for identifying our latitudes and longitudes. And then there's the geoid, that sort of approximate surface of the Earth that's oddly defined. Why do we have this geoid? And the way to think of this geoid is it's kind of like our mean sea level we used to use as our base, and it's extended into the various continents, sort of under or over the continents as a reference height. A geoid is defined as a surface where the pull of gravity is at a specified constant, and each country can specify a different constant for their geoid. And the idea is that it's like a sea level height if you didn't have currents and waves and wind and changes in density and all these other things that really affect sea level and make it a not very good surface. We originally thought the sea level was a good surface, but because of physical variation in the Earth, the sea isn't at the same level various parts of the Earth, even from one coast to the other. So we had stopped using this sea level or mean sea level measured with tidal gauges and started using a geoid in the last 30, 40 years. It's a much better, more stable surface, right? Horizontal and vertical datums are linked. They are developed in parallel, so we typically measure horizontal datums, horizontal positions as I described in the last lecture, and then we have vertical measurements at that set of points and sometimes at a denser set in between, but at least at where we have the well-defined horizontal measurements for a lot of those. We're going to measure the vertical elements too, relative to the ellipsoid and the geoid. And just as there's been an evolution in horizontal datums, we have various vertical datums to keep track of. And this is confusing. It's the cause of a lot of errors in GIS. So this horizontal datum, as I said earlier, establishes a reference ellipsoid at that mathematical surface and then points on that. And at the center of that ellipsoid is the mass center of the Earth with a equator and a principal meridian. In the vertical datums are reference surfaces that are known as geoids. It's an imaginary surface with a given gravitational potential, but they're all referenced relative to that horizontal datum, that ellipsoid, and its mass center. So we have to develop the horizontal datum, really, before we can develop the vertical datum. We used to set horizontal datum benchmarks, so survey out and measure the locations of things, and then do what's called leveling surveys. So we would measure the change in height across the surface of the Earth to say how much taller it was at one location than at a tide gauge from where we started. We don't do that anymore. We use GPS because we can get accurate positions in all three dimensions, so our longitude and our heights within minutes much more accurately. We don't have to haul up the equipment and measure from the nearest coastal point the changes in heights through time. We don't have to do these leveling surveys across space, because at each turn of the leveling survey we accumulate error. We make small measurement discrepancies, and by the time we get to the middle of the country, that error has compounded so that our measurements aren't as good as they could be. The reason we've come to this system and we don't use a sea level based system is that the old one, the one prior to the 1980s, was this National Geodetic vertical datum of 1929, and started a bunch of benchmarks at well-measured tidal gauges, and then they surveyed inland with these leveling surveys. But they found that if they went east to west or west to east or even up the coast, there were persistent differences that couldn't be ignored in the sea level heights along the edge. The sea wasn't at the same level. And so by the 1980s, they knew there had to be a better way because it just was inconsistent. And that's when we adopted a geoid, or gravity-based measurement. Well, why do we use a gravity-based measurement, and how do we use it? Well, we have to realize that there are these equipotential surfaces, and you might think of them as the pull of gravity being the same strength along these surfaces. It's not truly the definition. The definition has to do with the energy required to go from infinity to this location. But really the best way to visualize it is to think about this being an equipotential surface. So the pull of gravity is at a certain strength. As you go further away, the pull of gravity gets weaker until when you're out in space, you can float around. So orthometric heights are always measured from a geoid constant value up to whatever our height of interest. Now you might say, why don't we just use the ellipsoid? Well, it's kind of obvious, because here we have the equipotential surface for the pull of gravity that's not following the ellipsoid, and it generally doesn't follow the ellipsoid. That would mean all sorts of odd things, like you could have water flowing uphill because the geoid doesn't match the ellipsoid. And so we have to pick a surface and then measure up from that surface. Otherwise, if there wasn't a geoid, if this followed the ellipsoid, it would all be great. But that would mean the Earth didn't have any mass density variation through its whole surface, which isn't a physical reality. Now, in 1927, we could get away with using these leveling surveys from the coast because the measurements weren't very good and our data were very sparse. By 1983, we had a lot of repeat measurements from a lot of different directions and more accurate measurements, and the discrepancies came to the fore. So when we looked at the NAVD88, reference to just one tide gauge versus the NGVD29, so this takes all that new data in between, we could look at the difference between these tidal gauges due to these differences in the density of the Earth and the differences in the equipotential surface. So this is 125 centimeters, and this is 4 centimeters. So from here to here, we had more than 1.2 meters, about 4 feet difference in the mean sea level, because the pull of gravity is stronger here and it's buckling down the sea. Also, things like changes in salinity and persistent currents and bulges will affect the mean sea level. So the NAVD88, which was the last leveling survey-based geoid, they fixed it to just one station, said we're going to fix the equipotential surface relative to measurements at that one station, and then measure the equipotential surface along with survey data across the entire continent and get heights that were consistent with one equipotential surface. So this NAVD88 was the first modern datum, the vertical datum, the North American vertical datum of 1988. It's a reference to this single tide gauge in the Gulf of St. Lawrence, so that we have a consistent set of height measurements. Now, after that, with GPS and better geoid measurements, we increased our frequency of height measurements and height datums. So there's the Geoid 03 that we fixed with the original NAVD88. We used that with the Harn GPS, the 1996 NAD83. But then by the NSRS 2007 version of NAD83, that horizontal datum, we got an improved datum. And we improved datums for the 2011 version, and we're working on data measurements. So just like we improve our horizontal measurements with GPS, we're using GPS plus other measurements to improve our geoidal height measurements across the country. And we get enough of them, we get a new geoid, and that changes the heights of everything. So you have to know which geoid a height is measured against. And typically, if you know the NAD83 2011, they're going to use this Geoid 12B. So you can calculate between versions what the vertical height shifts are due to a better measurement of the geoidal height. Because remember, I'm measuring my height relative to the geoid, so if the surface doesn't vary, but I have a different estimate of the shape of the geoid here, I'm going to get a different height. Now, luckily, or thankfully, these 2003 to 2009, they're on the level of 10 centimeters, so 4 or 5 inches. In some places, they're much larger than that. And then from 2009 to 2012, or the NSRS 2007 version, NAD 83 to the 2011 version, they only change by sub-inches for most places. So again, we're measuring the orthometric height from the geoid up to the surface or wherever we're interested in measuring a height. There's this ellipsoidal height and this geoidal height, which are sometimes reported, but our orthometric height is from the geoid to the surface, and that's our standard mean sea level height. Now, we're always measuring at right angles to every intervening equipotential surface, so this wiggly line is on purpose. Now, a straight line measurement, a normal measurement up to the surface, varies by millimeters or tens of millimeters. So for most of us, we don't have to worry about that. So if you read a definition and it says it's at right angles to every intervening surface, it's because they have to be in their calculations consistent. But for most GIS as a practical matter, it doesn't make a difference. The distance is almost the same. How do we get these geoidal surface? Where we have instruments, right, that we either drag across the surface and this actually measures the change in the pull of gravity inside. There's a set of magnets on springs and the mass gets pulled down, so there's more tension on the springs. Some of them use photons on photonic measurements of particles that go up and down. There's various methods to get very precise measurements of the pull of gravity, but you have to calibrate the system and take it to a location and make sure it's working, and then do quality control afterwards. Another set of measurements we can make from satellites. Now, they're a little bit broader scale because they're integrating the mass over a patch below the satellite, but there have been a couple of satellite measurement systems, one by the US and one by the European Union, well, several actually, to measure the pull of gravity from space. And so we have this really increased network of measurements, and so these are the distance to the nearest well-measured benchmark. You can see some states like Minnesota and Wisconsin or Florida have really measured lots of places. Right? You can put these on planes, you can drive them across the surface, whereas other states like Nevada or Utah have a relatively sparse measurement network. Right? And so they really don't have as good a vertical datum, but nonetheless, it's fit and the geoid is provided for you, so you can give you, if I know the latitude and longitudinal location from GPS, I can get the geoid height above or below that spheroidal surface. I can actually look up this distance, right? And then once I get this distance, I can estimate what this distance is from the GPS measurements. So we have a set of measurements. Again, how much the heights change with vertical datums. Right, so they change here by tens of centimeters down to a few centimeters. So if we have the latest versions of the geoids, they don't vary much. Right, so from 2 to 7 centimeters from 1996 to 2012, or 1 to 3 inches. So the geoid shifts. But for most measurements, unless you're really building water structures, that height is not that great a shift between the various datums, right? Heights change substantially between, though, the two families of datums, the NAD 83 and the ITRF WGS 84. And you can remember why that might be. We have different ellipsoids. And the different ellipsoid locations means relative to the geoid, the height's going to vary quite a lot. Right? Those mass centers are calculated in different places. So between different versions of a datum within the same family, the heights don't vary much. Between different datums, they do in different families of datums. Right? This is a real issue because a lot of our data in GPS are collected in ITRF or WGS 84, and we translate them to work in NAD 83 here in the US. So we're going through this conversion, and if you pooch this conversion, if you collect these and think they're these, your heights are going to be way off, as are your horizontal locations, right? So here are the shifts, right, up and down between one system and another. For the NAD 83, Mine's the local mean sea level from 1960 to 1978. Now, this begs the question, if I'm working on the coast to these various locations, how do I actually calculate relative to the actual local mean sea level? And you have to go to the tide gauges and calculate the differences. Now, there's an example in the book I won't go over here, but basically you have the NAV 88 height and the mean sea level height. And so if you have any of your data that's relative to a datum, you have to then calculate what's the offset. Right? In this case, this is at 4.22 relative to the local datum, and this is at mean sea level is at 6.73. So my zero here is difference by 2 feet. So the station datum is down here, there's a zero down here, but my heights here in the NAVD 88 are going to be 2 feet lower than the mean sea level height. Right? This is 6.7, this is 4.2. So I have to be careful when I'm doing any design to take in this difference in height. Okay? And you can see, well, what's the offset? It varies across the coast from 2.51 to 2.6 to 2.62. So these difference in heights across the coast vary but slowly. So I can just get the nearest tide gauge when I'm doing any measurements near the coast. Okay, so in summary, horizontal datums shift through time. More lately than early on. So these shifts here are in the centimeter range. Datum shifts between family of datums are large and have stayed large, at least between the unaligned families. So the NAD83 we use here in the US is very different from the WGS84 or ITRF, and that's the most common mistake, is working in one when you think you're in the other, right? Orthometric heights are now our standard heights, and they're measured relative to a geoid. And these geoids change in measurement through time, not as much as the horizontal measurements, but still, they change through time. We have to make sure that we're using this orthometric height correctly, right? Heights are measured relative to a geoid, a measured gravitational equipotential surface. The sets of measurements are taken together, the ellipsoid and the vertical datum, and so there's families that are used together. The big difference we have to pay attention to for heights is between the WGS ITRF and the NAD83. If you make a mistake with these, you're making a mistake of 2 to 6 inches. If you make a mistake between the NAD83 and the ITRF, or NAD83 and the WGS84, you're making a mistake of 1.5 to 3 feet in height. So we have to be careful in using these datums, particularly in the switch between the families of datums, in both the vertical and the horizontal shifts. Hope that helps.